Okay, following on from my last video of summing series, this one is going to involve some binomial expansion examples, which is the other type that you can get. These are much less common. It's usually geometric, but I need to cover this as part of the course. So whenever you have your binomial expansion one, you'll be asked to do something algebraic beforehand, which is seemingly unrelated, but is actually a result that you're going to need to use in the expansion question. So even if you can't do this this part of the question, you can still use this result in the second part. So part I is to show that 1 plus e to the I theta is identical to this expression here. So what I'm going to do is just look at this complex number, 1 plus e to the I theta. I'm just going to draw a quick little Argand diagram here. E to the I theta is a general complex number with modulus 1 and argument theta. So it's going to lie somewhere in the unit circle, and I'm just going to put it there just for argument's sake. So that's e to the I theta. I'm now going to add 1 to that, which means it's going to move across here by 1, and that is now the complex number I'm interested in, 1 plus e to the I theta. And if we complete the rhombus, then we can get an idea of exactly what's going on here. So each of those lengths is a length of 1, because e to the I theta has a modulus of 1, 1 has a modulus of 1, 1 has a modulus of 1, and then I'm taking this length here is 1 plus e to the I theta, so that's also got a modulus of 1. So the argument of e to the I theta is theta, so therefore that angle there is theta. And what I'm doing is I'm taking this rhombus and I'm actually cutting it directly in half. Okay, so to find the argument of this point here, I need this argument here, which hopefully you can tell is just half of theta. So that tells us that the argument of 1 plus e to the I theta is a half of theta. Okay, so it's a half of the angle of e to the I theta. The other part that we need to know is the modulus. It should hopefully come out to be 2 cos for half theta. And what we're going to do to find the modulus is just look at this triangle here, which has 1 plus e to the I theta as one vertex, the number 1 as another vertex, and the number 0 as its third vertex. This length here is 1, this length here is 1, and this angle here is going to be pi minus theta. And the reason why it's pi minus theta is because this angle here is also theta, and angles in a straight line add up to pi, so therefore that's pi minus theta. And we're going to use the cosine rule to find the modulus of 1 plus e to the I theta. So the modulus of 1 plus e to the I theta squared is equal to 1 squared plus 1 squared plus 2 times 1 times the cosine of the angle in between them. Minus there, which is pi minus theta. So that's kind of a squared equals b squared plus c squared minus 2ab cos c. The 1 squareds come together to give that. And cos of pi minus theta is the same as minus cos of theta. So that becomes plus 2 cos of theta. Factorize out the 2. Gives me that. And then I can replace the cos theta here with 2 cos squared of theta on 2 minus 1 to give me 4 cos squared of theta on 2. Okay, the minus 1 from in here cancels with that 1. This is now 2 cos squared of theta on 2. Combine that with the 2 at the front gives 4 cos squared theta on 2. Square root both sides, and we get then that the modulus of 1 plus e to the I theta is equal to 2 cos of theta on 2, which is what we want. So I haven't got room here, but in an examination situation, you would summarise what you've done and explain why this then equals that. The important point is that result. Okay, is that result. We're going to need to use that in the question. That's why this question is scaffolded and asked that first. So on to the actual question then. We're told that C is this finite series and S is this finite series. And what gives it away that this is a binomial question rather than a geometric question is the binomial coefficients. Okay, in this case, I've put it as NC1 and NC2. This would be NCN, which of course is 1. But sometimes you'll see them written as what look like vectors, but they are still the combination function. So as always with these questions, we calculate C plus IS. So that's going to be 1 plus NC1 cos theta plus I sine theta is e to the I theta, plus NC2 e to the 2I theta, plus dot dot dot, plus NCN e to the NI theta. Okay, so cos 2 theta plus I sine of 2 theta is e to the 2I theta, taking the NC2 out as a factor. And then the NCN I've put in here, and then we've got cos of n theta plus I times sine of n theta is e to the NI theta. What you now need to recognise is that this is a binomial expansion of 1 plus e to the I theta to the n. And it's not necessarily obvious that it is that at a quick glance. But if you binomially expand this, you will get to this series. Furthermore, use the hints from the previous part of the question to help you. We've been asked to be dealing with 1 plus e to the I theta, so why not expect 1 plus e to the I theta to come up? And that's exactly what we've got. 1 plus e to the I theta has now come up. So now that we've got this series, C plus IS is this, we can now use the result from part I in there. So I'm going to replace the 1 plus e to the I theta with this thing. And the reason why that's beneficial is because this is a single term. So you can apply the power n to each of those parts separately, and you won't have n plus 1 terms. So therefore this is going to equal 2e to the half I theta cos of a half theta all to the power n. Now I can apply the n. So that's going to be 2 to the n. E to the n on 2 I theta cos of n of a half theta. And now finally, we can state that C is equal to the real part of C plus IS, which is therefore 2 to the n cos of n on 2 theta times cos to the n of a half theta. Okay, that's a real part of this. Don't forget that this is cos of n on 2 theta plus I times sine of n on 2 theta. So taking the real part, that's real, times the real part of that gives this. And similarly, S is the imaginary part of C plus IS, which is going to be 2 to the n sine of n on 2 theta times cos to the n of a half theta. And that's C and S. Do have a little bit of a harder question as well. So again, the format is very similar. You start with a show that part of the question, and if you can't do that, you can still use this result in here. So in this case, it's now show that 1 minus e to the I theta is identical to this thing. And we're going to get, well, I'm going to do it slightly differently this time. I'm going to say this is 1 minus cos of theta minus I times sine of theta. And I think I'm going to go the other way, actually. I think I'm going to go from right to left. So let's take the real part of this is going to be 2 sine squared of a half theta. And then the imaginary part is going to be minus 2 sine of a half theta times cos of a half theta times I. Sine squared of theta, that can be written as 1 minus cos of theta. Yeah, so that is 1 minus cos of theta. And then 2 sine of a half theta, cos of a half theta is sine theta times I. If you're unsure of where that's come from, just recall double angle formulae, and I'm reversing that process. So cos of 2 theta is identical to cos squared minus sine squared, which is identical to 1 minus 2 sine squared of theta. So this implies then that sine squared of theta is identical to 1 minus cos of 2 theta. So in this case, 2 sine squared of a half theta must be equal to 1 minus cos of 2 times a half theta, which is just theta. And then for this one here, I used the fact that sine of 2 theta is identical to 2 sine theta cos theta. Again, replacing theta with theta on 2, we can then see that the 2 sine of theta on 2 cos of theta on 2 must be equal to sine of theta. So we've got that one. So these two therefore are identical. Therefore it's true. Part 2 of the question. Here's our C and here's our S. Show that C divided by S is cot of a half n theta when n is even, and find a similar expression for this when n is odd. So we're going to do as we always do, C plus IS. And this is going to equal 1 minus, and we can see that the binomial coefficients this time are in vector form. Okay, but they are still just the binomial coefficients. So NC1, cos theta plus I sine theta is e to the I theta. NC2, that's going to be e to the 2I theta, minus dot dot dot, plus minus 1. NCN is just 1, and that's e to the ni theta. And this is identical to 1 minus e to the I theta to the n again. If you're unsure where that's come from, you can reverse engineer that and expand the bracket and get back to this, or you could just consider what was asked in the earlier part of the question. We are now using this. So because that is now here, I'm going to take the definition of that and plug that in its place. So that's going to become 2 sine of a half theta into sine of a half theta minus I times cos of a half theta. And that's all to the power n. This is not quite in the form ready for Demas Theorem, so I'm actually going to take out a factor of minus I from that. So that's going to become minus 2I times sine of a half theta. And that's going to leave me with cos of a half theta plus I times sine of a half theta. So if I were to bring that minus I back in, I'd get the minus I cos of a half theta here. The minus I and the I would combine to give a positive 1, which would give me back to my sine of a half theta here. And now I can apply the n to all of this. So that's going to become minus 2I to the n times sine to the n of a half theta. And then because this is of the form cos phi plus I sine phi, I can apply Demas Theorem, and that's going to become cos of n on 2 theta plus I times sine of n on 2 theta. Now from there it matters if n is real, if n is even or odd. If n is even, then minus 2I to the n is real, because I'll be raising I to a positive even power. So that's going to become real. It might be negative, it might be positive, but it will be real. And that's important, because when I want to extract the real and imaginary parts of this, I need to consider which parts are real and which parts are imaginary. So if n is even, then I get C is equal to minus 2I to the n sine to the n of a half theta times cos of n on 2 theta. And S is going to be the imaginary part, which is minus 2I to the n sine to the n of a half theta times sine of n on 2 theta. And that's because this is real. This is then the coefficient of I, and this is the coefficient of not I. So we have enough information now to calculate C on S. And C on S, that's going to cancel, that's going to cancel. We're left with cos of n on 2 theta divided by sine of n on 2 theta, and that is cot of n on 2 theta as required. However, if n is odd, then minus 2I to the n is purely imaginary. It's purely imaginary. So going back to this, that is an imaginary number now. So C is going to be the imaginary number times the imaginary number, that's the real part. So it's going to be minus 2I to the n sine to the n of a half theta times sine of n on 2 theta times I. Okay, n is odd, therefore this is imaginary, so that is actually real. And S is minus 2I to the n sine of to the n of a half theta times cos of n on 2 theta. The problem is this sine is actually going to be the imaginary part times I, bearing in mind the imaginary part is the part of an expression which multiplies by I, therefore I actually need to divide that by I as a correction. Okay. And C on S, therefore, again, that's going to cancel, that's going to cancel. I'm left with I times sine of n on 2 theta divided by cos of n on 2 theta over I, times top and bottom of that by I. That will cancel, that will give me a minus 1, and then I've got sine over cos, which is tan. So it's minus tan of n on 2 theta. And that's the solution for when n is odd.